it's a later response, and that's kind of expected, right? Depending upon the object speed, my response will be earlier or later. But this information alone is not good enough for your vision sensor to detect the collision. What we do is we then use the programming capability. So if we program our device, then what happens is, as I keep applying different voltage pulses, the device current keeps decreasing, or inhibitory response shows up. Sorry. Now, if I combine the two, so if I have this looming object and at the same time I keep programming my device, then the photocurrent is trying to increase and this guy is trying to decrease my device current. So these two kind of creates a non-monotonic escape response, which is very similar to the locust. And you can see that the point of collision detection is always before the collision point. And here we show that irrespective of the speed of the object, we are always able to detect the collision before it's actually going to happen. Now, since we're only using a single device and we are combining the sensing with compute, we are able to achieve remarkable energy efficiency of few nanojoules to perform this difficult computational task. And this work, if you're more interested, you can find more information in our Nature Electronics paper, which were published last year. Now, moving ahead, I will probably skip this part because this is an Optic Society talk. So I will go to the talk, which is more about, another vision application, which is related to stochastic resonance or noise enhanced detection of the signal. Typically, we consider noise to be a nuisance. We don't like noise in our devices. And that's why we always want to either increase the signal strength in order to get a better signal to noise ratio, or we want to reduce the noise floor for my detection so that the signal can be discovered. And you can do it using lock-in amplifiers, low noise amplifier, noise filters, and many of these things. But these are extremely hardware intensive, bulky, and energy inefficient. But if you look into the nature, you will find that, and of course you cannot deploy these instruments in remote location. Let's say in a desert or in deep underneath the ocean. You cannot take a lock-in amplifier there, right? There you have to derive the inspiration from the evolutionary success of animals, which actually survive in very resource-constrained environment. And here is the example of a paddlefish. So the paddlefish actually is found in the Mississippi River in US and Yangtze River in China. These rivers are actually very muddy, so you can hardly see anything once you are under the water. The paddlefish actually feeds on a very small zooplankton called Daphnia. Now, the paddlefish cannot really detect the Daphnia by seeing it, but when the Daphnia moves, it actually creates a very weak electrical signal, which is detected by this electroreceptor in paddlefish, which is called the rostrum. Now, typically, you will assume that, the paddlefish is able to find Daphnia up to a distance of 50 meters when there is no noise. But then a group of scientists actually did a behavioral experiment where they added a little bit of noise to the signal of Daphnia. And they found that if you have too much amount of noise, then the paddlefish cannot find the Daphnia at all. But with the right amount of noise added to the signal, the paddlefish was able to find Daphnia even at a distance of 100 meters or 75 meters, which means that the chances of finding a Daphnia by the paddlefish simply increased. And then they found that this electrical noise was created by the group of Daphnia or the zooplankton, right? So therefore, this army of Daphnia is actually betraying the outpost Daphnia, which is essentially trying to survive. This phenomenon is called the stochastic resonance, which in this case is used by the paddlefish to locate the prey. But if you really look into the sensory neurobiology, you will find that this phenomena is available for a wide variety of species to either escape from predators, or find mates, or kind of find prey as well. In fact, stochastic resonance can be found at all scale, from geographical scale, from the formation of Earth's ice ages every 100,000 years, to the opening and closing of the ion channels inside our brain or in the neurons. So what is stochastic resonance? Stochastic resonance is just that if you have a weak periodic signal, which is below the detection threshold, you cannot detect that signal. However, if you add white noise to that signal, because white noise has got all sorts of frequencies, then occasionally the signal that you are not being able to detect can cross the threshold. And then if you have a thresholding sensor, then the signal can be detected. So that is the idea of stochastic resonance. So we thought that, okay, this has been demonstrated in sensory biology, but can we actually use it in some kind of a solid state devices? So we did some experiment with MOS2 photodetectors. So here, as you can see that we have an LED and our MOS2 based photodetector. If we apply a periodic signal to the LED, this signal is detected by the photodetector at the same input frequency of the LED. As I keep decreasing the intensity of the LED, at some point of time, the photodetector is not able to detect the faint LED signal, which is kind of acceptable because every photodetector will have a detection threshold beyond which you cannot detect that signal. The next question was, can I use the phenomena of stochastic resonance to detect otherwise invisible signal? So here what we did is, so here is the experiment where we have a weak periodic signal. There's a photodetector over here which is based on MOS2, and you can clearly see that there is no signal detected over here because this signal is actually very weak. So therefore, even after a long time, I cannot really detect that signal. Now, instead of, and if I use a noisy LED, of course, there is no signal. So therefore, nothing gets detected, right? Because there is simply noise. So therefore, either the signal by itself, which is very weak, not the noise, kind of creates any kind of information in the sensor. But what happens if I combine the two? So if I have a weak signal and then I add white noise on top of that, then what starts to happen is that I start discovering the weak periodic signal, which was otherwise undetectable. And so therefore, this is the phenomenon of stochastic resonance. So what is really happening is that when the LED signal is below the threshold, of course, I cannot detect that signal because it always remains below the threshold. But if I add a little bit amount of noise, then sometime the signal starts to cross the detection threshold of the sensor. And if I do it over a long period of time, then the signal starts getting detected. If I add a little bit more amount of noise, I can probably detect it much earlier. But if I add too much amount of noise, then of course the noise floor increases so much that everything is again completely lost. So therefore, you can see that without adding any noise, you can never discover the signal which is below threshold. If you add too much amount of noise, then also you will not be able to discover the signal. But with the right amount of noise, you can detect signal which are below the detection threshold of your sensor, right? And you can do it at very low energy consumption, right, of tens of nanojoules. So this is essentially the demonstration of stochastic resonance in photodetector, but the idea can actually be expanded beyond, sensor to chemical, biological, thermal, and radiation sensors as well. Beyond photodetector, you can go to any of the sensor, and the idea could be used to detect signal which are below the detection threshold. I don't know how much time I have. I will probably wrap up here, and I will probably have to have more discussion with you guys if you have questions. So what I have shown you are two examples essentially, where I have shown you that how biology can inspire the next generation of the sensor design, right? So natural design can really help us to make our next generation of artificially intelligent or smart devices even smarter, and at the same time making sure that they are very energy and area efficient. So that is what we are trying to do. We are essentially trying to exploit these unique optoelectronic, electronic properties of these 2D materials to develop the next generations of sensors, computing and storage devices, and then drawing the inspiration from nature or animal brains to bridge the energy gap between artificial and natural intelligence. So, these are some of our recent publications. But if you're interested, I could talk a little bit more about the things that I discussed, or if you have any question, I will be happy to take it at this point.
Thank you, Dr. Das, for a wonderful talk. So I have one question that you have used Al2O3 as the gate oxide. So is there any advantage of it? Like why specifically Al2O3?
Right. So I think there are two reasons. Number one, alumina is actually a high K dielectric. So
Hello, can you hear me?
yeah, I can hear you. Can you hear me? Can you hear me?
Yeah, we can hear Saptarshi. Sudipto, can you hear Saptarshi?
Yeah.
Okay. Yeah, Saptarshi, go ahead.
Yeah, so the reason for using alumina is that it's a high K material. So SiO2, which is typically used for most of the device fabrication, has a dielectric constant of 4. Alumina has 10, and high K dielectric actually helps me to get better electrostatics in my FETs. So that is number one. Number two is alumina, we can also kind of do certain tweaking with our ALD processes or do some kind of a post processing in order to create these trap states, which can help me to essentially trap these carriers, and that allows me to perform this kind of a photo gating applications, right? I mean, the persistent photoconductivity that we are seeing is because of this carrier getting trapped in my alumina. So these are the two purposes that the alumina is serving: a high K giving me better electrostatics, so I can actually use and at the same time I can make it thinner. I mean, thinner any oxide you can make,
Okay.
but better electrostatics and the ability to store charge in the oxide, which gives me this memory capability for both optical as well as electronic memory.
I have a question.
Okay. Thank you.
Yeah, Dr. Das, thank you for a very nice talk. And my question is regarding the stochastic resonance in the photodetector system, what you mentioned. It's very intriguing that you would be able to kind of mimic some of the aspects of a biological system. So these resonances, how sensitive are they to the dimensionality of the system, what you use? And if at all you could create such kind of resonances, not only in terms of an electrical readout, but also kind of an optomechanical readout or something like that. Is that a feasibility? You may want to comment.
I mean, there is actually a good volume of work where people have used optomechanical system for stochastic resonance.
Yes, exactly.
There are actually some papers out there.
Yeah.
So, I mean, we haven't worked with mechanical system, but there are actually some of the good papers. I can send you those papers if you would like to read.
Yeah. Now, why I'm asking that is that given the fact that your dimensionality of your system is already quite low, you would be able to then couple your electronic readout or electrical readout with the mechanical readout. Is that something you would be kind of looking at, or is that actually something kind of complementary to what you're doing? I'm just wondering.
I mean, I will be very happy to look into that. I mean, I have really not invested time or resources in looking into coupling mechanical system or MEMS system with our nano device.
Yeah.
I think your point is very well taken, that if we can make these MEMS devices and put our optoelectronic sensors on top of them, then I could really benefit from both ends. So I totally agree. Yeah. Absolutely, that you can really exploit those systems. I personally haven't looked into that, but that is really something in the future we might actually consider.
Very interesting, very interesting. On a related note, if you also cool your system down to very low temperatures, for example, if you look at these stochastic resonances at extremely low temperatures, let's say in a vacuum chamber, then your system also becomes probably like extraordinarily sensitive to the environmental effects, because as I see, the experiments what you showed were at room temperature, if I'm correct, and that would really push the limits down to quantum limit or something like that. That would be fascinating to look at.
I agree. I totally agree with you. Yeah, I mean, there's a lot to explore in this area. I mean, there's a very recent work of ours, and I think one of our colleagues actually told me that, I mean, probably you can try these stochastic resonance experiments. Initially, we were not sure that whether they will be successful, and then we were actually were quite pleased to see that, it actually works.
Wow.
And I think we're moving towards, looking into some of more complex or trying to answer, one of the more complex phenomena, because this is stochastic resonance have been out there almost for the last 30 years.
Yeah.